We will finish up Chapter 21's topics in tomorrow's lesson, but first let's take a look at a recap of what we've looked at. If you have a charge moving in a magnetic field, it will experience a force. We also saw that a current-carrying wire, which is just a bunch of moving charges that are in a magnetic field, will also experience a force. For that, we had that our force was equal to ILB sine of theta. The direction of both of those forces can be found using our right-hand rule. Today, we're going to finish up some of the other topics, and anything we don't get to tonight, we'll talk about in class. But we're going to look at the demonstration we saw today that a current-carrying wire can create a magnetic field. We'll find out, first of all, how to get the value for that. To be able to determine what's happening in these magnetic fields, we're going to need a second right-hand rule to determine the direction of the magnetic field created by our current-carrying wire. There are only two right-hand rules altogether, and so some of you may find this one to be easier than the first one. By knowing that we can create magnetic fields from current-carrying wires, we will find that wires actually apply forces by incorporating our past topics in with our new topics from this video. The magnetic field created by a wire. Anytime you have moving charges, it's going to create a magnetic field. There are two different geometries that we will look at. The first one in this video will be a long, straight current-carrying wire. We will, in class tomorrow, then look at what loops of current-carrying wire do. And we saw demonstrations of both of those in class. A long straight wire will create a magnetic field that has a magnitude of mu sub naught, which is a constant known as the permittivity of free space, and you will find this on your AP equation sheet. It's equal to 4 pi times 10 to the negative 7th Teslas times a meter per ammeter. The magnetic field then is just mu sub naught times the current in that wire divided by 2 pi r. With the magnitude in mind, the r represents the distance that you are away from the current-carrying wire. So as you move further away from the wire, the magnetic field decreases. The direction then can be found using our second right-hand rule. In this right-hand rule, your thumb will indicate the direction of the current, and you will place your thumb along the line of wire. Just like you're then grabbing that current-carrying wire, you will then wrap your fingers or curl them around, and the direction in which they curl will represent the shape of the magnetic field. To draw the current coming out of the page, I'll place that with a dot. And this will be my current. The current here is indicating that it's coming directly out of the page. The magnetic fields, which I'll show here in purple then, form concentric circles. They start and go around like this and get bigger and bigger. The direction of this magnetic field can be figured out using my right-hand rule. My current, again, indicates the direction that the current is traveling. Imagine a wire that is sticking straight out of the page, so the current's coming directly at you. And the direction of the magnetic field is shown by my fingers. My fingers on my right hand indicate the direction in which I'm going. So if my current comes out of the page, my magnetic fields are traveling along the outside. Up at the top, that's going to be towards the left. At the leftmost part of the page, I'm going to rotate my hand around, and I can figure out that the direction of the magnetic field is down here. As I get to the bottom, for this, I keep rotating my hand, and so my fingers are curling in this direction, and so my magnetic field underneath travels in this direction, and then last but certainly not least, over On the right, it's going to travel upward. Each of these lines then shows the same magnetic field strength. So as I look here, this all has the same magnetic field, this has the same magnetic field, and this has the same magnetic field. It's dependent on the distance that you are away from your current. So the distance out from my current is going to indicate how big my magnetic field is. In class, we got to see the effect of a current-carrying wire on a magnetic field. Now, the Earth's magnetic field is facing in this direction. The current in my wire is traveling along in this direction. And just as a reminder, from in class, we saw that if I increase the current, we get a deflection of our compass, and that's because the magnetic field has changed, or there's been a new magnetic field, and that comes from my wire. For my right-hand rule, my second right-hand rule, my thumb indicates the current, my fingers, and as they curl around, indicate the direction of the magnetic field. Because the current in the wire is traveling this way, I will grab the wire and know that my magnetic field is underneath going in this direction. So that means that the magnetic field that's in the wire is traveling right here. So the wire B field is traveling in this direction, while the Earth's magnetic field is this way. The vector addition of these two gives us a northeastward turn, and that's why my compass turns northeast. Goes from north to northeast. If I bring this up above the wire, just because of my right-hand rule says now that my magnetic field above the wire is going in the exact opposite direction. When I grab that and place that above, I get a movement towards the other direction. And so it's just because of the magnetic field created by this wire that we get the changing of my compass needle. And if I remove the current, there is no magnetic field created, and so the Earth's magnetic field takes over. We saw this in the demonstration today. We can then use this to see the effects on charges or other current-carrying wires, because if this wire creates a magnetic field, it can then cause a force on another charged particle. So a long straight wire has a current of 3 amps. We can figure out the magnitude of the magnetic force and the direction of the magnetic force on a particle that is moving parallel to that wire. The particle has a charge of 6.5 times 10 to the negative 6 coulombs and is moving parallel to the wire. So both of them happen to be traveling in the same direction, the current and this positively charged object. The speed of that particle is 280 meters per second. First things first, because I'm looking for the force on a charged particle that is moving, I'm going to use QVB sine of theta. But instead of being given B, I have to solve for it. The equation for that is just taking our magnetic field equation we just received, mu sub naught I divided by 2 pi r, and substituting it in. If my speed is 250, I will get a speed of 2.18 times 10 to the negative 8 newtons. As far as the direction of the force, for this, if my charged particle that is positive is traveling upward and my B field here is to the right, my magnetic force is going to be back along the radius towards the current carrying wire. And so the magnetic force is along that radius towards the wire. Knowing that a charged particle experiences a force, we can then look at a wire, a current carrying wire, and seeing what happens. Now, each of these current carrying wires is going to create a magnetic field. But using our right-hand rule, our second right-hand rule, we can see the direction of the force. We can then see the direction of the forces on each of these wires. When the currents are in the same direction, it's an attractive force. when the currents are in opposite directions, there is a repulsive force between these wires. And so if you have forces between two wires, currents in the same direction will attract, while currents in the opposite direction will repel. Tomorrow we'll be taking a look at a problem similar to this, and so if you look in your book, it's conceptual example number 10 in chapter 21. It wants to know about the net force in a current carrying wire exerts on a current carrying coil. And the question that it basically asks is the coil attracted to or repelled by the wire? So this wire here, we want to know, does this wire make this loop attract or repel away? Based off of this, I have two currents that are in the same direction here. I2 travels the same throughout this. But I2 at the top and I1 are in the same direction, so these two are going to attract. I1 and I2 at the bottom, because they're in opposite directions, are going to repel. And so an attraction and a repulsion, it seems like they might cancel out. But distance is going to matter in here as well. The current that is going in the same direction is closer to I1 as opposed to the current going in the opposite direction of I1. Because of this proximity and the fact that this current is closer, the total loop or current coil will be attracted due to the net force on this system. We'll take a look at this tomorrow in class. This will be our problem that we'll look at. So you can get some heads up by looking at the conceptual example in the book. But we'll do this one in class. And this will just about finish up chapter 21 for us. We will then be moving Monday into electromagnetism.